Okay, so here, so by the way, so I explained, last time I explained regression weighting as a solution to the optimization problem, right? And one thing I didn't tell you is that actually, instead of using this one, you can replace it by delta I. If you use this one, that is called empirical likelihood. Okay. And empirical likelihood weight and regression weight are equivalent asymptotically. So asymptotically no different, but finite sample is slightly different. And there's actually a lot of other classes too, but another one is, for example, you can also consider something like this. This one. So they are all similar class. I mean, classy read class. And anyway, let's move on. So now we're gonna move on to the general theory. So this is the estimating equation we'll use if we don't have any missing data, right? If we fully observe y, I will just use this one. Under the existence of missing data, we use imputed estimating equation, right? Which based on sampling, Monte Carlo sampling from the conditional distribution, which is often called prediction distribution. So prediction model or predictive distribution or imputation model, right? Model means it's a model, but here we are not really talking about the model. We have a specified parameter, so imputation distribution maybe. Okay, and then this parameter, right? This parameter is the model parameter that we use to generate imputation. And this model parameter should be estimated, right? So from a certain equation. So let's say that we have this kind of equation. Okay. And then how to, so now question is how to estimate the variance, right? So how to estimate the variance, variance of the solution. Okay, how to estimate the variance of the solution to this equation. So two approaches. One is the linearization approach. That is the section 4.3, which is this section. And another one is the replication method, which I plan to cover shortly. So basically, if this parameter is known, suppose, right? Suppose this model parameter for imputation model is known, then it's easy, right? You just worry about estimating. So there's no uncertainty in ahead. But in practice, this parameter is estimated from the sample. So there's a sampling error in it, right? So really the problem is how to reflect the sampling error of the eta head, right? Sampling error of the eta head. So psi is sometimes called a parameter of interest, right? Parameter of interest. And eta is the parameter that we use to estimate the parameter of interest. So that is the nuisance parameter. So basically, to estimate psi, we need to estimate eta first, right? And so how to reflect the uncertainty in the noises parameter is a critical problem in statistics. Okay, so huh? Not beyond the sample is a general well, I mean, it's about how to so that originally Gong and Samanigo, I think Samanigo, right? He's in UC Davis. He probably tired. That paper is 82 some 78. So well, anyway, so this paper, this is published in JASA, and this paper, I mean, many estimation problem has this kind of structure, and then it's not really not just the imputation. I mean, suppose a certain parameter requires information about another parameter, right? And then how to reflect the uncertainty. I think this is a pseudo-like method, something like that. I don't remember exactly, but good method. Anyway, there's so many different pseudo-like, so I cannot really. Well, okay, but here we are only considering the context of the imputation context. So then we can write it. I mean, we already covered this using an example, but I'm just reviewing. So basically, we write it, right? We write the conditional expectation of the original estimating function evaluated at parameter estimator, current parameter estimator, and then this is a random variable, right? So this is random variable, and so we need to reflect the uncertainty, and so we want to apply the Taylor expansion. So the Taylor expansion for equation 10, right? The Taylor expansion as a function of eta, right? You fix everything and just view it as a function of eta hat and do the Taylor expansion, right? So that is the first part. And then now how to take care of this, right? How to take care of this. The tip is think about what kind of equation we have for this eta hat P, right? So eta hat should be defined through an equation, estimated equation, which is this one, right? So you start from and then you can take another Taylor expansion on this one around the true value, right? So then you have this one. So then basically you can so basically from here, from 12, basically compute the form, right? So this is actually approximation. Compute form something like partial derivative u hat p eta null, right? So you can write it here. You move this to outside, and then take the inverse to get this one, and then plug in, so that this guy can be used to replace, to get rid of this one, to obtain 13. So that is the solution. So now, again, it's just a linear combination of the two estimating functions, right? So you have original estimating function, and this one is the another estimating function that estimates the eta, right? And so this is just a linear combination. The coefficient is particularly determined this way in order to remove the dependence on eta, right? In the first order. So idea is if you take the partial derivative of this guy with respect to eta and take expectation, it becomes 0. Okay. And so then once you obtain this one, you plug in and then essentially write everything individually. So as a summation. So then this guy is a function of, so this guy is IID because the original data itself is IID. So it's a function of IID random variable. So that's why it is IID. So then you can estimate the variance, right? So that is the basically the idea. And this is just a linearizing the equation. But we are so this is not the end. We need to use this one to derive the sandwich formula. So that is the next step. So the variance estimator is basically so this guy is, so if I write it this way, this is L, right? Linearized U by L. So this is the variance estimator of the U by L. The middle term. Okay. And then this guy is the partial derivative of the U bar, right? That is the same. So that means this U bar, by the way, this U bar L here turns out to be some of the QIs. So that's why we use actually. So okay. So we can actually just normalize it. I mean 1 over n, so that we can make it sample mean of the QI, and then basically this guy is just the Q bar and the U bar. Okay. So U bar L is a QI. So that you can obtain the variance estimator like this, and then we need to see, now the question is, what is the partial derivative of this guy? So which is, so we need to think about what is the partial derivative of the Q with respect to psi. Turns out that this is the first component. So the differentiation can go inside to U, right? So that is the. I mean, if the differentiation applies to the second component, it's more complicated, right? You have evaluating the expectation is. But here, the first component is just the inside. Because this Q itself is what? Itself is a conditional expectation of U psi given Y I OBS, right? So because Q is defined this way. Actually, UI. Okay. Q is defined this way. So if you take the partial derivative with psi, it's just differentiating the unit, right? So which is this one? So that is the sandwich formula. Okay. And now, yeah.
Here, like in the estimation procedure, we typically need to use MCEM to estimate impact first, right? And then having that, use MCEM again to estimate size.
Right.
It's basically two MCEM.
Yeah, two-step procedure. Well, okay. So for computing eta, you have an EM algorithm. Right. For computing psi, it's just a one-time expectation.
Okay.
Right. You don't update further. Okay. So now let's move on to another example. So this is kind of ANOVA example, right? You have a sample is partitioned into several groups. So, for example, in the household surveys, so when you take care of the missing data, I mean, when you think about model and missing data, you should first think about what kind of data is this? Is it business data or household data or education data? Different. Agriculture data, they are different. And what do you mean by that? Well, especially, for example, the survey of company. And survey of household. They are totally different nature. Why? Because if you think about company, and what would you measure? Like a revenue, right? I mean, how sales, these kind of things you will be interested. And then the sales of companies are quite different, quite skewed, very skewed, right? Most of the companies will lie in very small scale. I mean, so many companies like a small restaurant, right? Cafe, coffee shop, they are companies. And how much they sell, how much money they make. Maybe just a little bit, right? It's not really a lot compared to Apple, Google, Facebook, right? These companies will be huge, right? So then you cannot really assume that Apple and coffee shop are IID. No, it's a wrong assumption, right? It's totally wrong assumption. However, household, how much money you make and how much money? Is it, well, I make more money than you guys, but it's not really, 1,000 times, right? Maybe I make three times more than you, but it's not really 10 times, 100 times, not like that. Companies are actually huge difference, right? So in that sense, you may assume, okay, well, still, household, if you partition, make a cells like a age group, okay, and gender of household or race. So once you partition it, then characteristics within the group will be relatively homogeneous. Okay, so this kind of assumption is we can say roughly reasonable. I mean, okay.
So in this model, we observe SG, right?
So SG is actually just the index. So actually there's a X is a categorical, you can say.
Right.
So X is like if you think of ANOVA model, right? If you X is actually X1, XG, and X is XG equal to 1 and 0 if, okay.
Yeah, but my point is we observe groups, right?
So this is observed, right?
Right. So if the group is
The group is, right, group information is observed, right?
yeah, but if the group is outward, much more challenging.
Right. Yeah, sure. Yeah, right. So the group information is observed, but so here we are. So X is just a categorical, and then Y can be subject to missing this. Okay. So then, in this ANOVA model, I mean, so that means. So this is vector, right? And then xig equal to 1 and 0 if unit I belongs to group G and otherwise, right? And so and then we know belongs to one and only one group. So I cannot belong to both male and female, right? Impossible. I mean, I should belong to only one group. I mean, I cannot become age 20s and 30s. No, right? I mean, you should belong. So then basically the bottom line, the idea is you have okay. So mutually exclusive and exhaustive. So exclusive means that one cannot belong to two groups same time. Exhaustive means that every element should belong to at least one group, right? Should cover all. That's okay. And then in this model, so in this regression model, what is the yi hat? So the model, let me say, maybe I should. So, okay, yi. So y is a scalar. Right? So this is another model. And then what is xi is x1i, i1, xig, right? And so the group partition. And what is the beta? Beta, so this is 1 by g, and this should be g by 1, right? And then this one is mu1, mu g, right? And so then if we assume missing and random and things like that, then beta hat. So what is beta hat? Is x prime. We used this notation before, so let's use this notation again. So that is the another way of saying this is right. So that is actually mu hat 1, mu hat g. where why? Because this guy is a G by G matrix, right? This guy is a G by G matrix, and basically diagonal matrix, right? Because you cannot really belong to the same so two different groups at the same time. So it's just a diagonal matrix, and then it's just a summation, right? Summation of the category. So that is a numerator, denominator, and numerator is the summation of the y's in that category, right? So that's just this one. You have a group indicator, and then numerator is just summation of y among the respondent in the group, and denominator is the summation of the group, right? I mean, of the respondent. So that means your best predictor is just the mu hat G, right? So yi hat will be mu hat G, where I belongs to the group G. Okay. So that basically take care of so leads to this form 16, because end of the day, so you observe yi if delta equals 1, you don't observe, then you just predict it, right, for that group. But because of the residual property of the residual is the same as replacing by the predictor, and so you get this one. My point is that you can safely replace it by the predictor, by the property of the residual, right? So you can, so this is the already predictor, right? And this is, you can say by the property of the residual, you can replace the observation by the predictor. So this is just the sum of the predictor, always. And then here's a formula, right? Remember the linearization. So what did we obtain in the regression example? It's actually regression, very similar to regression example, right? I mean, you have a predictor and residual times the weight. The weight should be the weight for the respondent, right? That is the linearization formula. So we actually get the same result here, because in the ANOVA model, predictor is just a mu G, right? And then you have a residual. And then what is the weight? The weight is actually weight is greater than 1 because so this is using only respondent. So remember, this guy is a sample mean of the respondent. Delta I, xig, delta I, xig, yi. So for y, you basically inflate. You here. So originally you have an ng, but we want to compute divided by the among the respondent. So the weight actually is ng divided by rg, where rg, okay, I didn't really say what rg is. Okay, so rg is a delta I xig.
Here the order xig are dummy values.
I'm sorry?
The xig are dummy values.
xi is dummy variable, right?
Yeah, because in the regression, it is not that variable to be divided by xi squared.
Okay.
Like you write it, third chi. So in the, yeah, in the denominator,
Denominator, right, right. So it's here, it's a xij is dummy variable. So that basically, so it's a very quite useful trick because you basically predictor plus residual times the weight that you for the respondent, and that gives a good shortcut formula. Okay, so that is basically take care of the section 4.3. Now let's move on. Replication variance estimation. So so probably you guys heard about Jackknife and Bootstrap, right? Knife and Bootstrap. So this is class examples. So replication variance estimator is a class of the method based, including Jackknife and Bootstrap. The idea is you use some sort of the simulation type approach to do variance estimation. You don't want to compute the partial derivative. So idea is basically you want to decompute the estimator. So you have a estimator, right? You have an estimator. This is, in this case, it's just a sample mean. And then somehow if you can cleverly choose the weight and then recompute using the weight. And so this is too general. Let me use this Jackknife example. So what's going on? Well, basically the idea of Jackknife is you delete one. Okay, to delete one element sequence. So the superscript k means that you are deleting k, unit k. So if you delete k, unit k, that means your weight when I equal to k should be 0. Okay, so then because you delete the other weights the other elements are also affected. So then if your summation, so originally you can think of this way. So originally your weight is equal. Okay, originally your weight is just 1 over n or equal, and you want to delete one, but still want to achieve this constraint. Okay, so you still want the sum of the weight add up to 1 for each replication, but you want to one element to be deleted. That means you increase, right? You have other weights slightly bigger than, larger than this original weight. Well, okay. So what's the big deal? Well, let's see what is going on here. So yk then is 1 over n summation. So basically sample mean for replicate is you are removing. So this is the summation of the whole sample, but you remove yk. So here there's no yk, right? Because you are actually add and delete. And then so that is the replicate. And then this one gives an interesting So this one is actually, you can write it as a ny bar and minus yk, right? So that this one becomes so you have a something like this. If you delete, then you have algebra something. So what matters is, so this deviation is actually turns out to be proportional to the deviation from the mean. So that if you take the square and summation over k, then you have a 1 over n minus 1 square summation right? And so then you can actually multiply something like here, both side. Then end of the day, you get variance estimator. So this is original variance. So original variance estimator. Original variance estimator is what? Right? This is your original variance estimator, which is this one. But you can, so you have an alternative way of computing. It's the same algebra. I mean, algebraically the same, but turns out that it is very interesting. So I will show you why soon. But here it's just for the linear case, it's just exactly algebraic equivalence. It's nothing really mystery. Algebraic equivalence. And now here, so what is interesting? So interesting part is actually this. So if it's a smooth function of the y bar, and then you compute the Jae-kwang and apply it, then it is actually equal to this algebraic. So symmetrically equal to this, which is actually linearized variance system. Why? So what I'm saying here is that I'm saying is so this is suppose you are interested in estimating the variance of a set hat, which is the g of y bar n. And then how to compute the variance originally? Well, we use Taylor expansion, right? So you have something like, okay, so something like this. So that is your Taylor expansion. Linearized. And so your variance, and then from here, you compute the variance. So that is g prime mu y square and variance of y bar n, right? So that is the usual linearization variance estimator, which requires computing the partial derivative, g prime. So to apply this one, you have to differentiate it, right? But this one here, this replication variance estimator doesn't do the differentiation at all. It just you just apply replication. So you first compute the replication y bar and apply, and then run the program, and then turns out that that is equivalent to this asymptotically. So why? Why? Okay. So, well, roughly speaking, so what is K? So this is and okay. First of all, I'm going to just use jackknife for now. So that is, remember, this is variance of y bar, right? And y bar hat. And so here, it's not really rigorous, but you can kind of see that this is big O 1 over n. Well, point is big O p. Point is it goes to the order, I mean, it goes to 0. So then you take the Taylor expansion over this guy. So here's a probably looks this well, this is a little bit interesting linearization, because you are linearizing with respect to a random variable. Y bar is random variable, but under some conditions, you can still argue. So as long as this guy, the radius goes to 0, okay, so in parity, you can kind of argue that this one, so that this difference will be something like dominated by this difference. And then from here, so let's just, so that means or okay. This is really rough, yeah, rough story, but hopefully it's probably I mean, this is a scalar. And this guy is, wait a second. So basically, this is the jackknife, right? We just use jackknife variance estimator applied to theta hat. This is a definition. So my jackknife variance estimator can be computed this way. So basically, what is this? We know the function. So it can be any known function, right? You have some similar function and plug in, then you output. So that means you can actually input same way you input k, right? Y by k. If you input y by k, then the output will be theta hat k. So that is basically purely computational thing, right? You can just compute it. But because of this behind relationship, because you can kind of see that this difference is bounded by, dominated by this difference. So you can kind of see that this is actually equal to Taylor linearization. And then that is actually really good news for government agencies like that, because they are just a government employee, right? That they don't really don't want to compute all the differentiation. For example, I mean, you guys are familiar with the differentiation, but sometimes it's not really easy, right? For example, if you have a ratio y bar, you have for example, you have a 4y, foreign vector. How to compute the variance of this guy? Or, right? For example, 3. Suppose you have this kind of estimator. Say, how to linearize it? Well, even statisticians, it's not, we can do that, right? We can compute partial derivative, but it's not really fun, right? But if you use jackknife, it's very easy, right? You just compute it. How easy? Very easy, right? So then you just apply it as you know the form. And so you basically create n replicate of zeta hat, and then apply it to the formula, and then give you variance estimator. So actually it can be automated, right? You have for example, all the tables. If you have all the tables, and you compute all the point estimators in the ratio and all this, standard error, computing standard is not really easy if you think about writing all the linearization, right? But jackknife is very easy. So that is actually, and also in our problem, missing data problem is also easy. We'll see soon. Okay. So basically, this is sandwich formula, right? So sandwich formula is based on linearization. So now let's discuss how we can use the replication method to compute the variance when the parameter is computed from estimating function, estimating equation. So psi hat is a solution to this equation, estimating equation, and then how to compute the variance of psi hat. All we know so far is this linearization, right? Sandwich variance estimator. But that's one way. Now let's use jackknife. Let's discuss how to use jackknife or Bootstrap to compute the variance. Well, the idea is very simple. Okay, let's apply the weight, jackknife weight here to the equation. So that is basically you have a weight. So we already know the equation, right? So the equation itself is we already know. So this is our equation. Psi yi equal to 0. This is equation. And now let's use equation, but change the weight, because currently the weight is 1/n. Now we can use the jackknife weight to obtain, right? So replicates. So use that. So for each case, right? For each case, I solve this one to obtain psi hat k for each k. And so then I have n of them, so I apply this to the formula. So that's nice, but sometimes solving this nonlinear equation itself is tedious, right? So one way, remember, so one idea is when you solve this one, use originally, okay. So originally you have an equation. And then the iterative Newton-Raphson, Newton method, right? Newton method uses this kind of u dot psi t inverse u psi t. Okay. And then you have actually double computation in the sense that for each k, you iterate, right, until convergence. And then you do it over n, over k, over different k. So you have a loop, right? You have a one loop here, another loop here. Okay. And turns out that you don't have to do complete until convergence. Actually, if you choose as an initial value to psi k, so this guy is what? The constant estimator already, right? Not for k. So you already know this one. And then apply to this form. So basically we are interested in what is this? This guy is a solution to this equation. But point is you use psi hat because you know this one. You use this as an initial value to do iteration, and then you have only to compute it one step. One step means you just do it once, no iteration. Once that is already enough. And furthermore, you can actually, so you don't even have to be worried about this one. You can just replace. So you don't have to change the weight here in the denominator. Well, if you think about it, if you use this one to the replication variance formula here, if you plug into equation 4, so if you plug this guy into equation 4, will lead to, so applied to 4 is algebraically, okay, no static, it's just algebra is equal to this one, right? Because you have this guy here, and this guy comes here. The notation here is so that means what? That means you have actually this guy corresponds to tau hat inverse, and the inside corresponds to the variance of the u you have. So that actually matches with the sandwich formula here, right? Because you have three terms, bread part and ham part. The bread part is exactly equal. Ham part, previously you use closed form solution. Now we can use the Jae-kwang inside to u function. So that's supposed to be essentially the same. Okay. So why? Okay, now this is the overall overview of the replication method, and now we're gonna move on to how we can apply it to our problem. So really, again, it's all about how to compute the variance with estimated noises time, right? And you have a noises parameter estimated, which is at the head in your estimating equation. How to reflect the variance estimation. Well, remember we already covered using linearization method there already. Now, when you apply linearization method, is computing the partial derivative, right, of two equations. It's not really easy. Now we are going to do the same thing without computing the partial derivative. So that's the real advantage. Okay, so the concept is this. So now you can just see that you have two equations, right? You have two equations basically. One equation given at head. Another equation is determining at head. That's it, right? You have two equations. So then it's just you can combine the two equations and do it jointly, right? So then from here you can directly apply replication method. Basically, for each replication, you solve this equation for the unknown parameter to obtain psi hat k and at hat k. And then use psi hat k to compute the variance. That's it. And so then you don't have to linearize, right? That's so simple. And let's see what it means using the example here. You don't really have to. So okay. So now I'm going to explain how to do Jae-kwang. I mean, how to use Jae-kwang for replication to compute the variance of the regression imputation. So we have basically we can call it two-step procedure. Step one, compute the replicate of eta head. Step two, plug in and solve it for psi. So basically the same thing. Step one, so the eta corresponds to beta head here, right? That is the model parameter, the imputation model parameter. So basically we use the replication rate to recompute beta head, which is basically solving this equation. And then apply. So my imputed value changes to reflect the parameter estimation. And then my estimator also uses the replication. And so use that, you can basically compute the variance estimate. Okay. Does it make sense to you guys? Clear?
This works for missing at the random
Okay. Actually, another. So the next example will be not missing a random. So we don't really require for this theory. We don't really require missing a random error. So we can, as long as under the correctly, as long as the model is correct, this should be valid. So here's an example. Basically, this is, I think, Y is binary. Right? Y is binary logistic regression. Bernoulli P xi beta, something like that. And beta x is a logistic regression. So this kind of problem. But we allow for non-missing and random. So the deterministically imputed estimator of the mean of y is this form, where you have for delta equal to 1, we observe yi. Delta equal to 0, we don't observe yi. So we want to compute the conditional property of y equals 0 given x and delta equal to 0. So that, but we don't know this model. So we use the Bayesian theorem, right, to obtain. So this is the basically you have two parameters, right? You have a property of this guy. Okay. What is pi? Sorry. Should be 1, right? Yeah. This should be 1, not 0. So then this guy is a property of y equal 1 given x delta hat, and this guy is a property of delta equal to 1, 0 given x and y psi hat. Okay. And so we do this is so in this case, see, if you are asked to solve the variance, derive the variance estimation of this kind of imputation estimator as a homework, you'll be very angry, right? Because so many parameters here, you know, you have how you want to linearize all that. It's very tough, right? But good news is that we don't have to, right? We don't have to if you can use computer. So basically, this is just a recap the EM algorithm, right? We already covered this. So E step, M step, right? We have a so E step, M step to estimate beta hat and phi hat, right? So point estimator. And conceptually, our goal is to okay, theta hat and phi hat to obtain theta hat I. Theta hat I is a function of beta hat and phi hat, right? And now what we want to do is to compute the replicate, Jae-kwang replicate over this nuisance parameter, and to obtain so basically, see, this is again, this is nuisance parameter, right? So nuisance parameter. So nuisance parameter means that the model parameter, right, for the imputation model. But end of the day, what you're interested in is computing the marginal probability y equal 1. That is the only parameter you are interested in. But this one with missing data, you have to use this kind of imputation, right? I mean this one. You use this imputation to compute, to estimate this, to estimate parameter. So that is this one. Now, instead of doing linearization, right? Instead of using linearization, the idea is okay. We can, even though completion may take time because we have to use EM algorithm for each K, right? For each K, but still doable, right? You can do. I mean, maybe R is not really good because R is not really good for repeated. I mean, loop, but I use Bootstrap and no problem. And anyway, any other some, I mean, conceptually still, now you can do parallel computing or high speed computing. So computation time is not really big deal nowadays. So basically, you can, for each case, you apply EM algorithm, compute that had K and it had K, and then plug it to your imputation estimator. And why? So one thing we should emphasize is that that's not, we need this guy. That means we need to use. That means we need to use the replication weight. So delta I yi plus 1 minus delta I yi hat k, where I hat k depends on some parameter. Okay, so model parameter is used in prediction, right? So then the replicated, so generalized version of the model parameter should be used to obtain the generalized version of the predictor. And then the imputation estimator itself also should use generalized version. So that the point is that we need to not just here, but also here to compute the Bootstrap, I mean, replication estimator. Okay, so now question is how we can compute it. Basically, we use the same EM algorithm using, you can, I mean, it's solving. So one way to compute the mean square equation is using EM algorithm, but if you have other method, that's also fine. But so solving this equation directly is difficult because you have here parameter here and the weight. So what you can do is compute fix parameter and solve it, update, and then update your weight. So that is the updating weight is the E step, and updating parameter here is M step. So that take care of the chapter 4, and I uploaded. So the exam will be Friday, right? October 21st, right? Something like that. 3 to 5 p.m. Snedeker 3105. And I have a, okay. I already uploaded the old exam, so you guys can take a look. So that's it, and we'll move on to chapter 5 next week. I'm sorry?
The weight after I take.
This one? No. This one.
Yeah, right.
1 over n minus 1, except for k.
Yeah. Right. So that is corresponding to Jae-kwang.
Yeah, Jae-kwang, right.
But if we use Bootstrap,
You can use Bootstrap, right?
Yeah.
Let me, actually, so you can see that, the disadvantage if you use, so here, Jae-kwang, right? Replication, Jae-kwang or Bootstrap is very good at computing the variance without, right? Because it uses the iterative method to compute. But the problem is that with the missing data, you may use EM algorithm. So you use, and especially the E step involves MCMC, right? And sometimes Monte Carlo sampling. And so for each K, the EM can be very slow. the EM itself can be very slow, and then you have to do it over and over again, right? For K. And so that could be disadvantage of the using frequentist. So Bayesian approach actually doing all these things together. So basically Bayesian approach. So we do like we do replicate. For each replicate, we find the MLE for each replicate, right? And then but Bayesian is actually doing all things simultaneously. So in that sense, Bayesians are more attractive when we have a missing data. So that you can see it next week.
So for each case, in that need one need to estimate this DNL. So this estimation are parallel to each other.
Right. So you can actually, if you can do parallel computing, maybe it's okay. Right. It doesn't really depends on other case, right? Because you can do everything parallelly. Okay. See you next week.